Hello and welcome back. If you follow the channel, you already know that my HP 9825, famously used by Mr. Fancy Pants in the HP catalog, recently died from a power supply failure that caused an overvoltage. The 5 volts temporarily became 13 volts, which is a big ouchie if you are a TTL chip. In the first episode, we repaired the power supply, but the computer did not boot afterwards. We then checked for signs of processor life in the second episode. We got the 2 clock phases, the reset signal, control signals for start and end of memory cycle. So the processor was not completely dead and was at least attempting to read memory. But we can already tell that something is very wrong, as the processor gives up reading memory after about 15 milliseconds of trying. Time to call in the HP Logic Analyzer for the rescue to see if we can get some clues about what is happening. I don't know that we escaped the Logic Analyzer on this one. It's trying to start up, but not starting up. Logic Analyzers are killer tools for debugging computer hardware, which allow you to capture all the ones and zeros traveling around in your machine. HP used to be head and shoulders above the competition in Logic Analyzers. The Series 1600 started as early as the 1970s. The first instruments are a hoot, literally displaying ones and zero on the scope screen. My 1607 here can capture and display a whopping 16 lines of 16 bits. But the one we'll use is the last iteration of the 1600 series, the HP 1670G from the 1990s. It's a great instrument to debug early computers, and we used it extensively for debugging the Xerox Alto and the Apollo Guidance computer. So we want to put the Logic Analyzer on the bus of the CPD processor, and it actually has 2 buses. One is the I/O bus, which is a traditional bus with 16 bits of data over here and 4 bits of address over here. But the bus we're interested in is the 16-bit bus over here, which is both data and address. So it's multiplexed, which is going to make our life very annoying. So sometimes it's data and sometimes it's address. The question is where to probe the bus from the machine. Not on these connectors, because these are hooked up to the I/O bus, would be the wrong bus. The processor, as you can see, is compressed, so you don't have access to the pins. However, over there is a remnant of a connector that was used in the first version of this machine, the 9825A. So if you take the keyboard off, you see that we have a whole bunch of connectors, and those were used for ROM cartridges, the optional ones that you put in the front of the machine, right here. But this big one was used for the system ROM in the A. The system ROM is a drawer on the side. In the B and the T, the ROMs are over here, so we don't need it. So my thinking is to find a connector that slides on there and use that to probe the bus cleanly. And I had a connector that could go in it, so I have all my 16 address and data bits, because it's A multiplex and B bidirectional. And then we have a few other control signals. And Carl, the master of the Logic Analyzer, we have set it up to demux the bus. We have address and data. Multiplexed buses are a pain in the rear end, if you ask me. When STM goes down, it should be an address. We looked at the actual memory schematics, and it appears that they trigger data when STM goes up, so earlier than this diagram shows. Multiplexed buses were used to save pins on a package and wiring on the PCBs. One of the worst offenders was Intel's Pin Challenge 8008 processor. Not only address and data were multiplexed, but the address itself had to be broken into 2 parts that were multiplexed too. Fortunately, our Logic Analyzer is clever enough that it should demultiplex the bus for us if we set it up properly. So address you should have on, actually that's wrong, address should be is
on the rising edge of SMT, which is what you wanted, right?
No, that's data.
Right?
No, you have it. You just have data and address inverted.
Oh.
And it's a negative logic bus, so we turn bus data and bus address. No. We'll see if that works. So reset this. I'm still hooked up here. and you run, and you go. No, it didn't catch anything. It didn't stop. Oh no, just stop it manually now.
Yeah. Yeah, there you go.
Yeah, 40, 40, 40, 40, yeah. But, okay. Yay, we got a trace at the first try. But how to interpret it? Fortunately for us, HP filed a patent on the 9825. It's 626 pages long, and it's much better than the service manual. In particular, it includes a full listing of the source code. They sure don't write patents like this anymore. Also, another HP enthusiast by the name of Craig Ruff had dumped the actual ROMs, disassembled them, and confirmed that it followed the patent code pretty closely. Here is Craig's disassembly from the actual ROM, matched with the source code comments from the patent. As expected, the ROM code starts at address 40 in octal, the reset point. Instruction reads 164041, which is a jump indirect from the address contained at 041 in octal. And of course 041 is the next address, and we should have our destination in it, and it says 10,000. So it should jump to 10,000. If we look for it a little later in the listing, we find it here. And yeah, sure enough, it says Control Supervisor Power On Routine is the beginning of the boot code. So what we can tell from this is that on boot, it should read from address 040, the jump, then 041, the address where it should jump, then jump to 10,000 and start executing from there. Excellent. So the processor is, we expect it to start at address 40, and then it should jump at 10,000. So 40, then it's reading where it has to jump, and it's not jumping.
Right.
Oh, you know what? It's reading FF.
Yeah, it's just sequentially getting FF back, getting garbage back from the ROM.
Right. So I guess this tells us processor trying to work and can't read
It's not getting valid
ROM.
instructions.
So you know what else we have to do? We have to look after the latch. So one would think the ROM is dead or something simple like that. Well, maybe, but we have a multiplexed bus, so accessing ROM is a lot more complicated than you'd think. There is a lot of ancillary logic involved. So unfortunately, it's time to bring on the elevator music for the ROM memory read cycle explanation. So here is our CPD processor with its address bus. It wants to talk to the ROM, but apparently it can't. However, because we have a multiplex bus, there are a lot more things going on between the two, in order to mux and demux the bus. The processor will first take control of the bus and put the address bits on. Since the address is going to disappear in the next mux step, we need to keep that in memory. For that, there's a latch, essentially a 16-bit memory chip. The processor activates the latch through the STM line, which goes through some mystery logic and comes out as STM prime. When STM prime goes down, the address is transferred to the latch chip. Now that it's latched, the processor can release the bus. The address is then split in two bunches. The less significant bit goes straight to the ROM chips. The few most significant bits of the address go to the memory decoder. The memory decoder is connected to each memory ROM chip via a select line and enables only one chip at a time for reading. In our case, we have a 000 at input, so the ROM 0 will be selected, which happens to be our boot ROM. But the chip is not fully selected yet. For it to output its data, its second enable line must be activated. All the ROMs are enabled via the STM prime line on their second select line. This time, the selection happens when the STM prime line goes up. Now our ROM can finally output its data. But it's not yet on the bus. The data flow out of the memory is controlled by a bunch of tri-state buffers. These will only let the data go on the bus at the appropriate time, once again driven by some mystery timing logic. Now that the data is on the bus, our processor can finally read it. So long story short, there are quite a few chips that could have failed in this chain and caused the problem. We have come to the conclusion that we don't think we read ROM.
Right.
So what's the next experiment?
So we're going to quickly check. The first thing it should be doing is reading from location 40, so bank 0 of the ROM here. This is the select line. We should see it go low to select the ROM. If that doesn't happen, the problem is this way in the logic for selecting ROM.
Right, or on the buffer out, right?
Correct.
So here are my ROM chips. This is the bank 0. And I am on ground and select, so that chips would be selected to read the code to do the startup, and it doesn't read anything, so we'll see. Yeah, it sure selected.
It did.
I mean, it's selected. It should have read 40. It should have read what's in location 40. We didn't get it out of the ROM.
That's right.
So
now the issue is what's coming out of the ROM. So let's get on the data bits and see what happens.
All right. So now we're going to look at 8 of the address bits and 8 of the output bits in the ROM to see if the address comes to the chip correctly, which we think it does actually, and if any data comes out, because definitely the processor cannot read any. Okay, got it. Oh, I got nothing. You get anything?
But I've got bizarre looking stuff on ROM address.
Okay, run number 2. You're good?
Good.
I don't see selection.
Okay. That's not legit either. So you think we're loading down the...
So, Zippo selected over here, and then some weird 101, 103, 105. It's counting. 107. We have the bits not correct. So we see garbage addresses on the ROM, and we're wondering if just the address doesn't get to the ROM at all. And the latch should trigger on the signal called STM prime,
which also selects the ROMs to read. So
which also the second select to the ROM. So I have added a probe in green over here. If I trigger it, and yeah, I'm on 5 volt, and STM prime, there is no latching signal.
And that should have been high, except for when it's going low to select the signal, and it's not a valid TTL level. Well,
no STM prime, and as we have just seen in the animation, this signal drives pretty much everything. So we have sure uncovered a fault, or so we think. So we're looking at one of the enables, which is STM prime, and STM prime should be mostly driven by STM, so that's start memory. And so I have STM on red and STM prime on green, and it's just one inverter gate, and we definitely see the memory access, but we don't see STM prime. And STM prime is latching everything, so it wouldn't latch our address. That would explain it.
Nor select the output.
Should we remove that circuit? And
yep.
So these are accordion things. Let's remove that. Remove that. Up. So that's the extra RAM board, and this is our, for now, malfunctioning main RAM and ROM board. Alright, so as we suspect either of those ICs, we don't know which one of the two it is. So I happen to have an HP branded, it's an 1820-1212, and another one, actually both are HP branded, 1820, 1367, so we have original HP parts. We don't know which one of the two it is, so we might as well replace the two. All right. You test it. What did it say, Carl?
Oh, wait. Well, it seems to work, but we don't know about the quality of the output signal, right?
And that's the gate that was failing?
Yes, that was the first one, right?
Yeah. To add insult to injury, both ICs tested okay on the breadboard, but in the circuit they were clearly misbehaving, so it's some kind of weird fault. So we're going to look if we are red recovered. 1, 2, 3. It did recover. Okay. It still didn't come up.
No.
So
we fixed some problems.
we did. So we have and then the recovery on both sides. We don't know which chip, but this is the output of the JK flip-flop, and this is the output of the NOR gate. So now it's good. Do you get anything on your trace that makes any sense?
Good stuff.
You get
Something different.
Yeah, it still goes 40, 41, 42, 43.
And he's, I don't know why it shows as 101, whatever here.
Okay, man, so that's the problem. If I have already 2 TTL fried, there could be an infinite number of them fried throughout the board.
Right, because we're still not seeing it.
But that looks a lot better.
Okay, so now why don't you go to the scope, put on the chip, and see the both chip selects and make sure they're both
Okay.
going low.
So we couldn't make any sense of what we saw on the state machine on the logic analyzer. So we turned it into a time machine to see kind of an oscilloscope trace of the signals. And on the bus, multiplex bus data and address, we see it counting up, but we kind of don't see any data coming down. It's little glitches. So at this point it's late in the day and it's getting notably more difficult. We might have multiple failures on the board, plus our logic analyzer setup is very suspect. We can't make sense of what we see, and we don't know what the correct signal looks like. So to disentangle stuff, we decide to cheat a bit and bring in my 9825T that still works. I have another one. So this way we can at least make sure we actually did repair STM prime correctly and get our instrumentation problem sorted out before we move further. So we have hooked up a second 9825 that works. We're cheating and trying to test the theory whether STM prime is half the frequency as STM, and a 1 and a 2 and a 3. Oh, and then it triggered on nothing. Try again. There you go. And the theory is been busted.
Refuted.
The myth is busted. That's the beginning, and it's starting. And we have one. This is STM. This is STM prime, and we thought the flip flop would delay something, but no. It's the same. So I think what we're going to do next is, now that we reached for the crutch and the machine that works, we're going to use the good machine to make sure we see if we can see data on the bus, if maybe our probing is bad. Make sure we can probe that machine correctly, see data on the ROM, and then look at the other one. But I'm very worried that we found at least 1, maybe 2 TTL chips that were bad, and we might have just a whole bunch that died.
Those were almost the first 2 we looked at.
Yeah, exactly. So how many other ones are there? So it could be a complete different signal that's bad in the memory selection. That might be catastrophic, to a point where there's so many bad TTLs in there that we can't repair.
And just the fact that we see the processor chip issuing sequential instruction fetches doesn't mean the rest of the processor is working.
Right. And yeah, we didn't see the processor actually release the line. That was worrying too. So there's lots of weird stuff happening on this bus. Oh well. Woo, I really needed the happy music to cheer myself up after this episode. And you guys have not seen the last of it. So see you soon for more adventures. Well, you guys missed another good one. I put the board back and it let the magic smoke out. This circuit burnt up. So, gee, we are getting more and more faults in the thing.